Hi everyone, hope you enjoy EDCON 2020 virtual edition. I'm Silur and this is a 15-minute detour into identity-based encryption and friends. On our agenda we have a short motivation and history for IBE. We're going to discuss the pros and contras for IBE, two instantiations, one with standard elliptic curve pairings and one with lattices. Then we're gonna talk about how to eliminate the trusted third party that's currently the pain point for IBE, which is why I selected this topic for this event. Then we're gonna address how to make signatures with a little abuse of protocol out of encryption, and talk about how to make hierarchical identity-based encryption later. So, how it all started. It turned out that when you put power back into the user, so when you are responsible for your own data, that responsibility usually manifests with responsible handling of your own keys. And in recent years, or not just with blockchain applications, since PGP and since RSA, it turned out that responsible handling of private and public keys are not very trivial for not tech-savvy people. So for this UX issue, Shamir in '84 asked for a public key encryption system with the twist that the public key should be arbitrary string. For example, your driver's license number or a passport number or just your email. So before sending out PGP emails, you don't need to exchange the PGP pub key because the email should be the public key for the recipient. So before talking about how generically IBE is constructed and get into specifics with curve pairings, we have to address how it differs or how it is similar to attribute-based encryption. So in both cases, we reversed the order of key generation. So instead of generating a uniform random private key and making the public key with some form of generator from this uniform random private key, first you ask usually a trusted third party how you want your public key to look like, and then with some trapdoor information your private key is gonna be generated for you that's gonna map into the public key that you asked for. But this can't be just one arbitrary string. It can be a set of attributes where you can define, for example, that all bus drivers with yellow hats can decrypt a message, and you can represent these attributes in a Merkle tree or something, or a hash accumulator, for example. So identity-based encryption is basically a form of attribute-based encryption where the attributes are so strict that these attributes specify the decryptor into one single identity. So the takeaway here is that identity-based encryption is just a form of attributes-based encryption. And for both, the common layout is that we have 4 polynomial time algorithms. One for the trusted third party, the setup with the security parameter, which will generate our master, secret, and public keys. Usually this doesn't really differ from usual elliptic curve Diffie-Hellman or Elgamal type keys, which we will see later. We have the interesting part is this extract algorithm, which with access to the master secret key and given an arbitrary string or a list of arbitrary attributes, an ID, can generate your secret key for you. And for the rest, we have the usual public key encrypt and decrypt algorithms with the twist that we see here, that for encrypt, now we don't use the public key, but the identity directly, which is the whole idea behind IBE. So use cases, why why it is useful besides having access to a public key without an additional step or an additional interactive step. One is asymmetric broadcast encryption. So broadcast encryption recently got some traction because of this COVID trauma, and will likely to get even more in the future, because broadcast encryption currently is mostly symmetric. For example, it's used in television companies where you can't store so many symmetric keys for your users, especially not in a dynamic way, because your viewers are usually stateless. And we've been waiting a long time for an asymmetric variant for this, because currently these keys are derived from a Steiner tree, so the user identities are some weird and not trivial arrangement, or arranged in a non-trivial way. Another example and Bonnet, for example, in the next slide, thought of is forward secrecy. So before you go to a holiday, you can generate an attribute or 7 attribute-based keys with timestamps attached to it. So timestamp can just be an attribute for attribute-based encryption, and you don't need the ratcheting and stuff, non-trivial protocols for forward secrecy, because timestamp here is just another attribute you have to attach to your keys, and if you lose your keys during your trip, you only risk the information encrypted by those. Intuitive key delegation. At the very end, we are going to dedicate one slide to hierarchical identity-based encryption. So you can even use attributes or identities where you say that anyone below this person or these attributes in the hierarchy can decrypt this message. So for example, your CTO at the company and everyone else, every developer under him in the hierarchy can decrypt a message that's sent to the development department, for example. But the catch here, why it's not very common or not common at all and not used at all in blockchain, is that it needs a trusted third party. So it's really not only unintuitive but really risky to have someone else generate your private keys for you, which can be actually mitigated, and we are gonna dedicate some slides for this. But before that, through practical constructions, the first is with elliptic curve pairings to stay in standard assumptions. So it's a chosen ciphertext secure constructions in the random oracle model. It's important. For the setup itself, we have 2 elliptic curves or an elliptic curve group equipped with a pairing, as usual with pairing-based constructions and the generator. For the master key setup, we have the usual process. We get a uniform random scalar from our finite field, and we mask the generator with this scalar to get the master public key. Nothing unusual. For the identity secret key, we're gonna use the previous master secret key. H1 here is a hash onto G1, so it's a hash function that maps arbitrary bit strings into G1. We map it onto the elliptic curve, and we also mask this point with the master secret key. For the ciphertext, we have a little similar to Al-Gamal type encryption, but we see here that for the generation of GID, we utilize the elliptic curve pairing here, so we lift it into G2, and we also and the other part, the second parameter of the pairing, is the master public key, because we have to bind to this MPK, because anyone can hash bob@evilcorp.com into G1, and you also have to bind this identity to the one authority that maps these identities for the keys, because infinite amount of keys can exist for both that Evil Corp otherwise, and you still need the authority of this trusted key generator to restrict the decryptor's identity. So just one slide for Cox. We know that there is a way to make identity-based encryption out of quadratic residues. Why I omitted the specifics here is that it works bit by bit. So it encrypts bits and in a highly inefficient way. It's a really cool theoretic construction, by the way, but we already know that it's highly inefficient and unusable in blockchain applications. So even if we would do it and sacrifice very decryption and encryption time, we will very soon run into out-of-gas exceptions had we implemented this. So because of this, the next construction I selected from the literature of IBE is a lattice version. And the reason for that is that they are highly parallelizable, quantum safe, which is not an unimportant thing in my opinion. And but because parallelization and quantum safety are kind of a religious war in crypto or within researchers, one of the most important takeaways is that hierarchy is easier to define. We're gonna see later that you define hierarchies with a twist on the extract algorithm that we defined prior to include some vectors, and representing elliptic curve pairings and samples for them in the form of vectors and operating on them are a little more inefficient than doing it with lattices, because with lattice primitives your trapdoors and keys are already in vector form. So for the construction itself, we have a uniform random lattice A0 and the basis TA, a short basis. This is very important for it. So the short basis will be our most important trapdoor information, because without access to this short basis, you will need the Lenstra LOAS or the BKZ algorithm to calculate short vectors in the lattice, which is assumed to be even quantum hard. So the TA will be our secret key for the trusted key generator, this short basis. For the other public parameters, we have two other uniform random lattices and a random vector in the finite field that we used to define our lattices. So this will be MPK. For the identity secret key, we also have a trapdoor sampling algorithm which I just replaced with TS here, because the original BBA construction used TS as a basis delegation sampling and the basis delegation problem, but since the original publication there has been many more efficient, smaller and even constant time trapdoor functions on top of lattices with better sampling and short. So yeah, let's see what the future have us for Ethereum on IBE, and see you next year. Bye.
All right, hi, I'm Henri, co-founder of Streamr. Welcome to this 15-minute talk, during which you'll learn what the heck are data unions and how you can start one yourself. So sit back, make yourself comfortable, and let's get started. So first of all, what is a data union? It's a framework for building applications that pay users for sharing valuable data. It's an implementation of a data crowd-selling pattern. For builders such as yourselves, it's a potential business or perhaps a way to liberate data from centralized monopolies. And from users' point of view, it's a way to earn by providing data. To give a concrete example, I'll show a ready-made data union called Swash, and afterwards I'll show how you can build a data union too. So one day, late last year, when the data unions framework became available in private beta, a team shows up in the Streamr community with an idea. They applied for a grant from the Streamr Community Fund and built Swash. Swash is a browser plugin that shares and sells your web behavior data anonymously and in real time. Most applications collect and sell user data secretly on the side, but this is the opposite. Its sole purpose is to collect data in a fully transparent, fair, and configurable way. We can see here I've earned 74 Streamr data tokens so far, which is around $4. With the plugin active, if I, for example, do a search on Google, the plugin produces data points on what I searched for and which results I clicked on. I can fully inspect the contents of all data before it gets sent, and there's an endless amount of privacy settings which I can tweak to something I'm personally comfortable with. With enough users participating, this kind of data would be interesting to web analytics companies, retailers for analyzing their competition, and well, maybe even crypto speculators to see what projects are getting attention right now. Of course, there are many kinds of data that can be shared and sold, from people using digital services to IoT and environmental sensing, such as weather or pollution data. Broadly speaking, there are two categories of end-user apps. There's dedicated apps like Swash, where data sharing is the main feature of the app. But the data union features can also be added on top of existing apps as a sort of side benefit. For example, imagine a Fitbit data union where the framework would be part of the Fitbit app and give the users the option to share and monetize their wellness data. Data unions are built on two main technologies. Of course, Ethereum, where smart contracts are used for storing and transferring value, as well as maintaining the data union state and doing all kinds of bookkeeping. Then there's the Streamr network, which is a decentralized pub-sub message broker for actually transporting the data from the crowd of data producers to the consumers or buyers of that data. Additionally, there's the Streamr Core web app that provides a friendly interface for setting up and managing things, and a marketplace where access to data streams is sold to interested buyers. What basically happens is that data providers interact with the end-user application, which is data union specific, like Swash, for example, and the rest of the components are part of the framework. The application pushes individual data points to the Streamr network. Buyers interact with the marketplace, the app, where they can purchase access to the data content and afterwards start receiving it via the Streamr network. The payment goes to the data union smart contract, which keeps a record of each user's cumulative earnings and allows the tokens to be withdrawn. The data union admin can set a fee, which is a way for getting compensated for developing and maintaining the app and potentially making a business out of it. The admin is usually the party who created the end user app, but could also be, for example, a DAO consisting of the data union members. This talk is more about how to use the framework than the details of how it works under the hood, so I won't go too deep into it, but perhaps worth drilling down for a quick look into the Ethereum side of things. One thing important to understand is that currently data unions can't run fully on mainnet due to high costs and lack of scalability. And there's two ways in which we've solved this. The currently in use 1.0 version maintains the data union state off-chain and uses an operator/validator model and has a Plasma-like interface for withdrawals, which means users can withdraw by presenting a Merkle proof of their earnings to the mainnet smart contract. Now, in 2.0, coming out later this year, the data union state is fully on-chain, with the parts that need scalability in a proof of authority sidechain run together by all the admins of the different data unions, and the token bridge built by the POA network guys bridging between the chains. Now, this should improve both usability as well as security of the system. So, but how do you actually use this? So there's basically 4 steps to creating a new data union. First, you set up your streams, then you deploy the data union smart contract. The most involved part is integrating the actual end user application, which is usually the data source and also acts as a wallet. And finally, you publish your data union as a product on the marketplace to start selling the data and earning revenue. So first, you need to figure out how to model your data into streams. Streams are sequences of messages, so you need to decide which events go into which streams. A typical approach is the fire hose, where a certain type of data from all users goes into the same stream. In Swash, for example, all web searches go into one stream, and YouTube behavior goes into another. Then you simply use the core UI to create the streams you need. You basically give them a name and hit create, so easy enough so far. Okay, now our streams are created, but they remain empty until we start sending data into them in step 3. First, however, we create the data union itself. So also using the core UI, we go to create new product and choose the type data union instead of the basic one, which is used for B2B data sales, usually. Now, we give our data union a name, a cover image, a description, and whatnot. And in particular, we bind the streams we created in step 1 to this product. So we're saying these streams contain the data for this data union. Then we set a price per time unit for subscribing to the data. For example, $1 per hour. The price can be defined in data tokens or pegged to USD. And finally, we set the admin fee, which is your percentage share as the admin for creating and maintaining the thing, and the rest of the revenue gets automatically distributed to the users. Okay, now we're ready to deploy the data union to the blockchain, and for this we need a mainnet transaction. The deploying address becomes the admin address for the data union. Cool. Now our data union exists, so we can start integrating the end user app, which allows people to join the data union and send data into the streams. So to do the integration, we'll be using the Streamr SDK for JavaScript, which provides easy-to-use wrappers for everything we need, including the data union's functionality as well as publishing data to the Streamr network. When your app starts for the first time, it should generate an Ethereum private key and store it locally. The key will be used to sign withdrawal transactions, for example, as well as to sign the data that gets sent to the Streamr network. Before you interact with the system, you create an instance of the Streamr client object and pass it the private key. Also part of the initial setup, you call a method join data union to have the user join the data union. You only need to do this once. This calls the default gatekeeping service that validates a secret that should only be known by your app. Now, you can replace the simple default gatekeeping with your own, for example, to include a CAPTCHA to defend against bots or something like that. Okay, now that the user has joined the data union as a member, we can start actually publishing data points to the streams by calling streamr.publish with the actual data payloads, whatever they are in your use case. Since the end user app acts as a wallet, you probably want to display the user's balance and earnings somewhere in your app. And you can easily query those with the getMemberStats function. Members accumulate earnings for as long as they want, and they can withdraw them from the smart contract at any time. The tricky bit is that the withdrawal, of course, requires a mainnet transaction. So the user needs to have ETH in their address to pay gas, which is tricky from a UX point of view. Now, for better usability, there's another function that allows the data union admin to sponsor the withdrawal by paying for the gas. They might cover it from the admin fee, for example. Needs to be said, though, that with the current, through the roof gas prices, users need to accumulate a fair bit of value before they can even cover withdrawal costs. But obviously, the current gas price situation on Ethereum will eventually be solved one way or another. I hope. Anyway, that's it. Our app is now fully integrated to the framework, including initial setup, joining, data production, and withdrawals. The final bit is to publish the data union as a product on the marketplace. So to do that, you go back to the core app and hit the publish button on your data union product and do another mainnet transaction. This makes your data union publicly visible and the data streams are now on sale. The public product listing shows stats about the product, such as member count and total earnings. People can now unlock access to the data by purchasing a subscription for a time period of their choosing. So that's it. We're all done with creating the data union. One thing though, as the admin, your job is to create supply and demand by marketing your app to users, as well as finding buyers for the data. You should also keep your data union tidy. And there's some supporting tooling available to, for example, kick out members who are no longer producing data. The framework is currently in public beta, so you can just go and start building. The best place to start is the docs, which you can find under the project website at streamr.network. And there's also a bunch of screencast tutorials coming soon. All right, that's the end. Thanks for joining this session. Keep building and stay safe.
Hey everybody, my name is Crain. I'm the CEO and co-founder of SuperRare, and today I'm going to be talking to you about NFTs, an unlikely catalyst for a revolution in art. So not many people know that art has a data problem. The Independent estimates that up to 20% of art in major UK museums might be fake. And this might be understandable with some of the older pieces in their collection. They might be hundreds of years old. How can they possibly actually know who created the art and when it was created? But this extends beyond really old pieces of art and goes into the contemporary art market. So just in general, getting good data about the market is really expensive, and you can't really be sure how high quality the data is. So there's a number of proprietary data providers. You can pay them a subscription and you can get access to their pricing data. For example, if you wanted to know, what was the average price of a Picasso that was sold last year and how many Picassos were sold last year, you'd need a subscription to one of these proprietary data sources. So this is the problem because it makes it very difficult to actually audit the data that they're giving you. In addition to that, auction houses, one of the few parts of the art market where they're required to have public data, are known for what they call chandelier bids. So these are bids that are posted on the chandelier in the back. So even when you're bidding on a piece of art, you don't actually know if you're just bidding against yourself and the auction house is facilitating that. So I like to think about NFTs as a simple standards-based solution. So late 2017, ERC 721 came out, a standard interface for non-fungible tokens. So for those of you who don't know, a non-fungible token is basically a token with a unique identifier. So you can say, here's this specific token. I can know every address that's ever had it. I can know every address that's ever placed a bid on this token. It's a unique object. I like to think about it like an internet artifact. And what's exciting about these is they're very simple, but also very powerful. So just because we can issue this unique object as a certificate of authenticity for a piece of art creates a public permanent record of the piece of art. And this is a really big deal for lots of industries, but especially art where provenance is so important. The value of a piece of art might change depending on who previously owned it. Or you want to see, what's been the average price for art of this type. We now have this public record of these pieces of art, and that's a big deal. So I kind of like to think about it like NFTs create identity for internet artifacts. So here's an example of a piece of art on SuperRare. This looping GIF was created by the artist Pack. It's now owned by Whale Shark, and he's put it in his vault. And you can see an amazing provenance history right there. So just one simple standard, just ERC 721 allows us to build all of this information on top of the standard. So you can start to, just by having the standard and having wallet addresses interact with these tokens, you can kind of build a lightweight identity and reputation system on that. So, you can know what type of collector is this, or, how often is this artist transferring works to different people. You can build a lot of insights on top of the fact that we have these standards and can see who's interacting with these tokens. So it's a super simple concept, but it kind of allows for this beautiful industry to evolve on top. And, if we look at the data, you can see that, the numbers are growing quickly. So digital art has historically been a subset of the contemporary art market. So it's estimated that 2019, the contemporary art market was about 16 billion and digital art was about 500 million. So a very small subset of that. And why is that? Because lots of the new art forms and new art that's being created is actually natively digital. And so using NFTs as certificates of authenticity for these pieces of art give collectors that, they've actually bought an original, right? The artists themselves digitally sign these tokens when they're created. So you can be sure, you can know that a certain address created a specific token. You can see what block it was created in. So you have just a rich set of data around the art piece itself that you never had before. And, you're looking back, there have been a number of attempts to build, communities around digital art markets, and they've mostly failed. But I think what we're seeing with these NFTs being used as certificates of authenticity, that it's actually different this time. So digital art looking into the future, what do we think is going to happen? So we're just seeing more and more digital art, or more and more art be natively digital. So GIFs, probably the most popular art form on the internet. Having certificates of authenticity for those, hugely powerful. AR and VR sculpture, this is something that doesn't translate at all to a canvas that you'd hang on your wall. So, having something like an NFT, make it so you can uniquely identify a specific AR sculpture created by a specific artist is hugely powerful. And then again, video, a format that's been around for decades, now has verifiably scarce certificates of authenticity. And in addition to just kind of like issuing these certificates of authenticity, these also allow for new models of patronage. So with SuperRare, for example, we pay 10% royalties anytime a piece of art's traded in the secondary market. And we think this is just the beginning. Lots of folks are starting to experiment with new models. And, this is all built on top of the fact that we do have this NFT, this unique object that we can track and measure. And then in addition, kind of similar to how Bitcoin is 24/7 compared to the old financial markets that are closed on the weekends, this art community is 24/7. It's already around the world, people interacting in real time. So what's next? There's a lot of work being done, this R&D, building out really nice UX experiences for in-home displays. So this is rapidly improving. I think over the next 2 years, we're going to see, people's art collections moving into their home. Additionally, there's been a huge proliferation of virtual reality galleries and exhibitions. And this was partially accelerated by COVID, but basically every art fair that was supposed to happen in 2020 had an online viewing room this year. So this kind of just sped up the timeline, in my opinion, almost 5 years. So the art industry is really starting to embrace digital. And what does this mean for collectors? I think because we have so much art moving online, there's more access. More people can go appreciate the art. You now can have anybody in the world with an internet connection go to a virtual exhibition. Whereas if you have an exhibition at MoMA in New York, you have to be in New York. So I think there's greater access to art, and this is really exciting. So if you want to get in touch with us, on Twitter, we're SuperRare_co, and definitely go check out SuperRare.co. We have a lot of amazing artists, and I'm looking forward to seeing you there. Thanks so much.